Welcome learners, I am Dr. Pawan Kumar. So today I will discuss with you how to find minimum weight spanning trees in weighted graphs. So first you must know that a weighted graph is just a graph with weights with non-negative weights assigned on its edges. That is, every edge is equipped with some real number, or which is usually in our sense we will take only non-negative real numbers. So weighted graphs arise from many real-world contexts, and they can provide a great deal of information about the structure of the graph. For instance, the age weights can just tell us that the strength of ties, or they could also represent the cost of the communication between two nodes. And so while constructing weighted graphs, there are many things we consider, and minimum weight spanning trees is just one problem where they arise naturally. So they just tell us how to reach from one point to another with minimum possible weight. So in this session we are going to concentrate on two fundamental algorithms that find minimum weight spanning trees in weighted graphs. These algorithms were given by great mathematicians, namely Kruskal and Prim. So let's briefly discuss the objectives. So first we shall talk about what is a minimum weight spanning tree, and then we shall describe the problem minimum weight spanning tree problem, and then we come to the Kruskal's algorithm, which just finds the minimum weight spanning tree in a weighted graph. And then we shall also see why this algorithm works correctly. That is, we shall prove the correctness of this algorithm. Next, we shall look at Prim's algorithm, which is also minimum weight finding tree algorithm. And then we also compare the performance of these two algorithms, how they differ in technique and otherwise. So we shall just start with a small graph. So just concentrate on this graph. It has 10 vertices. The graph is connected, as you can see. So it must have a spanning tree, right? You can recall that a graph is connected if and only if it has a spanning tree. So that is one characterization of connectedness. So this graph has a spanning tree, which you can find using say breadth first search or depth first search algorithm. For instance, if you apply breadth first search algorithm, then we get the spanning tree as shown here, the red edges. So now this is a spanning tree, but the problem arises when the graph is equipped with edge weights. So just let's look at the weighted version of the same graph. So this is the weighted version. We have just assigned some arbitrary weights on the edges. And now let's look at whether the existing spanning tree is still a spanning tree in this case or not. So that spanning tree is still a spanning tree because actually edge weights do not affect the structure of a tree. The connectedness remains intact, and also the tree is acyclic, so that edge weights do not create any cycle. But the problem is here not of finding just a spanning tree. We have to find a spanning tree with minimum possible weight. Okay, now what does that mean? You can see that the weights are there on the edges. So if you just count the edge weights on all the edges of the spanning tree, you will get some number. So that number is called the weight of the spanning tree. Now our aim is to minimize that weight, the total weight. So now the question is, does this tree has minimum possible weight? Let's see. So just concentrate on this age V7 V8. You can see that its weight is 5, and now look at the age V6 V7, its weight is 3. So if you just replace this age with this one, you will get another tree, and as shown here. Now what we have got, this resulting graph is still actually a spanning tree, because we have just deleted one age and added one age. So the number of ages remains the same, and the tree there is no cycle created, right? These two ages lie in a cycle, but since we have deleted the V7 V5 and we have added, so there is no cycle created. So the resulting graph is still a spanning tree, and it also has weight smaller than the previous one, right? So this is a spanning tree with a smaller weight. In fact, we can get even further smaller weight spanning tree. For instance, if you just look at the age V5 V10, and if you just replace this age with V5 V6, then also you get a spanning tree, but in this case the weight will be even smaller, that is 7 units smaller. So this is the tree that we get after removing V5 V10 and adding V5 V6. So this way you can actually get smaller and smaller weight spanning trees. Now the fundamental question is, does there exist a smallest weight spanning tree? The answer is very simple. Since the graph is finite, there are only finitely many spanning trees. So we can just collect all those spanning trees. At least theoretically it is possible, although we shall also see why there are problems when the graphs are in large size. But theoretically it is possible. We can collect all the spanning trees and just pick the one which has the minimum possible weight, right? So this is what called the minimum spanning tree problem. Let's look at formally. So a spanning tree T of a weighted graph G is said to be a minimum weight spanning tree if WT is minimum among all the spanning trees of G. So WT is just the weight of the spanning tree T. So that is, given any a spanning tree, if its weight is smallest, then that spanning tree is called a minimum spanning tree. Now what does the minimum spanning tree problem seeks? It just seeks to find a solution of the it just finds a minimum weight spanning tree in a given connected weighted graph. So as we have just said, this problem has a solution. You just collect all the spanning trees and just pick the one which has the minimum possible weight. So that way we get a solution. Okay, now the solution may not be unique. That is another concern. For instance, look at just this small graph. So there are 5 vertices here, and any spanning tree would have just 4 edges, and there are in fact 2 spanning trees here having the same weight. The trees are shown in red and blue color. Look at the tree on the left one. It has weight 2 plus 2 plus 3 plus 4, which is 11, right? And the tree on the right hand side also has the same 11 weight, right? And it is also easy to see that there is no spanning tree with weight smaller than 11. So both these trees are minimum spanning trees. So it is possible that the MST problem may have multiple solutions. Okay, now you may ask, under what conditions it would have a unique solution? So here comes the question. The answer lies here. If a connected weighted graph has all edge weights distinct, then it has a unique minimum spanning tree, and we shall now prove it. Okay, to prove it, we only need to show that we just prove it by contradiction. So we take that there are two minimum spanning trees, and we arrive at a contradiction to prove that there is this possibility is not there. So let's now prove it. So let T1 and T2 be any two distinct MSTs of G. Now then there exist edges E1 and E2 of G such that E1 lies in T1 but not in T2, and E2 lies in T2 but not in T1. And further we construct two spanning trees from these two edges, the trees T dash and T double dash. T dash is just obtained by T1 minus E1 plus E2, and T double dash is T2 minus E2 plus E1. Now we shall first show that these are actually spanning trees, and then we will arrive at a contradiction. So I'll just concentrate on T dash. So how do we get this? We have just deleted the edge E1 from T1 and added the edge E2. So there is no change in the number of edges. That means T dash has the same size as T1, and also T dash remains connected, because when the edge E1 is removed from T1, what we are left with two components, and those two components must be actually connected by some edge, and that edge is E2. So the connectedness property is also intact. So T dash remains T dash has the same size and is also same size. That means the size of T minus 1 T1, which is n minus 1, and it is connected, and therefore by a property of trees, T dash is a spanning tree. Likewise, T double dash is also a spanning tree. Okay, now the question arises, because E1 and E2 are edges with distinct weights. So there are two possibilities. First one is whether the weight of E1 is greater than the weight of E2, and then in this case what happens? T dash has a smaller weight than T1. Why? Because we have just removed a larger weight edge and just added a smaller weight edge. So T dash has a smaller weight than T1. Okay, in the second case, suppose E2 has weight higher than the weight of E1. So in this case, T double dash becomes a smaller weight than T2. So in either case, we get a spanning tree which has weight smaller than the weights of T1 and T2. But this is actually a contradiction, because T1 and T2 are minimum spanning trees. So there cannot be any spanning tree with weight smaller than the weight of these trees. So this shows that there is exactly one spanning tree when the graph has all edge weights distinct. Okay, so thus far we have seen that any spanning tree, the minimum spanning tree problem has a unique solution when the graph has distinct edge weights. And of course, if the edge weights there are duplicacy in edge weights, then there can be many spanning trees. Now the question arises, how to find a minimum spanning tree? For instance, theoretically it is possible that we can just collect all the spanning trees, but then choosing the one with the smallest weight is not feasible, say when the graph has large size. For instance, just look at the case of a complete graph on 10 vertices. You might recall from Cayley's lemma that this graph has 10 raised to 8 spanning trees. So this is a huge number. This is not practically enumerable. So one has to look for some algorithmic technique that can just give us the answer. So now first technique that we are going to discuss is due to Kruskal. Kruskal was a great mathematician. His name, complete name, Joseph Bernard Kruskal. He lived from 1928 to 2010. He received his PhD degree from Princeton University in 1954 under the supervision of Paul Erdos and Roger Linton. You might recall that Paul Erdos was a tall figure in mathematics, especially in graph theory. So Kruskal received the supervision of this great mathematician, and he also spent much of his time in Bell Laboratories. So this is a laboratory where you might know that the C programming was developed. So Kruskal just got the supervision of great mathematicians, and therefore he was able to, after just completing his PhD thesis, in 2 years he published an algorithm bearing his name, and that algorithm was known as Kruskal's algorithm. So this algorithm solved the MST problem. The idea is not very extraordinary. He just simply thought that you start from just an empty graph, that means a graph having only vertices, no edges, and we also call it a forest. So you start from a forest and keep on adding edges with minimum possible weight until you reach the required number of edges. So in this way, he just described the algorithm, and that algorithm is called Kruskal's algorithm. Let us formally see what this algorithm is. So the algorithm just takes a graph G as input. Initially, we just take a set T which is empty, and there is a while loop. So this runs as long as T has fewer than n-1 elements. So n is here the number of vertices in the input graph. Okay, now at each step we perform some statements, and these are: pick an edge UV which is not in T such that the weight of UV is minimum. Okay, once we have selected such an edge, then we check if U and V belong to distinct components, then add the edge UV to T. So we have to keep on repeating these statements as long as T has fewer than n-1 edges. So after termination, what we will get is a minimum spanning tree. Now of course, what is the guarantee that this algorithm gives the correct answer? So we shall shortly see, but let's look at first an example. So this is the same graph we just discussed in the beginning. It's a weighted graph. So initially the weight is 0 and T has no edges. So mod T is 0. So we just select the first edge to be the one which has the minimum possible weight. But there are two such edges, that is V1, V2 and V5, V6. So we can select any one of them arbitrarily. Let's select say V1 and V2, V1, V2. So we get this edge. Now the weight becomes 1 and T has just 1 edges. Now the next we select the edge V5, V6 because it is the second smallest weight. Okay, and then we have to select the edge weight which is equal to 2. So there are many such weights. We can pick any one of them as long as it does not create any cycle. So let's select say V1 and V3. So this one, and then we select V1, V10, and then V10, V9, and then V9, V6. Okay, so thus far we have selected 6 edges and the total weight is 10. We have to select only 9 edges, right? So next we select. Now we can now select the age, this one V2 V9, because this will create a cycle. The cycle, this V1 V2 V9 V8 V10. Okay, so the next weight with the same value is this one V6 V7. So we can select this one. Now we have 7 ages. Now we can select the age V3 V4 because it is the next smallest weight and it also doesn't create any cycle. Okay, so now there is one more age we have to select. We cannot select V2 V9, we cannot select V4 V5 also, because it will create another cycle, and that cycle will be V4 V5 V6 V9 V10 V1 V3, right? So we are left with this one V7 V8. So we select this age. So this way we got a spanning tree, and which has total weight 22. It has 9 ages. Okay, so now we come to the proof of correctness of Kruskal's algorithm. So why the algorithm works correctly? The statement is, in a connected weighted graph, Kruskal's algorithm always produces a minimum weight spanning tree. Okay, now how to prove this algorithm? We shall actually start with the output of the algorithm. So let the output of the algorithm is, say, some spanning tree T, and we shall compare the output with some minimum spanning tree, and we shall show that the output also has the same weight as any minimum spanning tree has. So that is the idea. So we start with some output, say T. First we shall show that it is actually a spanning tree, and then we shall show that it is actually a minimum spanning tree. So let's start the proof. So take a connected weighted graph GW with T as output of the Kruskal's algorithm. So initially T contains just n components, and each component contains a single vertex. That is, the T is actually a forest in the beginning, and at each step at most one edge is added. Now what happens at each step? Now when an edge is added, the number of components reduces by 1, because any edge that is added, that actually just joins two distinct components. So those components become a larger one, and the number of components reduces by 1. So when there are n-1 edge additions, what happens? We are left with just one component, and this means T is connected. So thus far we have proved that T is connected, but to prove that T is a cycle, T is a tree, we need to prove that T has no cycle. Okay, so that part is quite easy, because at any step the edges are added in such a way that no cycle is created, right? So by the way the algorithm is designed, T is a cyclic. So thus T is a spanning tree. Okay, and now we have to show that this T has the same weight as any minimum spanning tree would have. So let's now compare it with some minimum spanning tree. So first let us call the edges of T as E1, E2 up to En-1. Right. So these are the edges which are chosen in this order, right, in the specific order. And let T star be any MST with the first k edges matching with those of T. So in general T star could be any MST, right? There could be a possibility that there are no edges which are matching with the edges of T, but we are just assuming a case, so that k could also be 0 here. In that case there is no edge matching. So T star is a spanning tree with first k edges matching with those of T, and we can further assume that k is as large as possible. There is no harm in this, because if there is such an MST, we can always just pick the one for which k is as large as possible. Okay, so now what we have, the edges E1, E2 up to Ek belong to T star, right? But Ek plus 1 does not belong. Now there are two situations. If k is just n minus 1, then all the edges from E1 to En minus 1 are part of T star, and T star cannot have any more edges. That means the weight of T and T star are the same. So T becomes a minimum spanning tree. But in another case, when say k is less than or equal to n minus 2, what happens? Let's see. So in this case, T star plus Ek plus 1 just contains a unique cycle, and let this cycle be C. So this is just one property of a tree. If T is a tree and E is some age not in T, then T plus E always contains a unique cycle. So T star plus Ek plus 1 has just one cycle, and we call this cycle C. Now C is a cycle which is not part of T, right? C does not belong to T. Therefore, there is some age of C which is not in T, and let this age be called E. Now since E is not in T, that means E is not equal to any of the ages of T. So E is distinct from E1, E2 up to En minus 1. In particular, E is different from Ek plus 1, right? And this means E actually lies in T star, because E lies in T star plus Ek plus 1, but E is different from Ek plus 1. So E actually lies in T star, right? Now we see that from these two edges, E and Ek plus 1, we can construct a new spanning tree, and let us call this spanning tree T dash. So which is just constructed by removing the edge E from T star plus Ek plus 1. So again, this is a spanning tree. There is nothing special about it. You can easily show this. Now it is a spanning tree. Then the important question is, the weight of Ek plus 1 is less than or equal to the weight of E. Now why it is the case? Because while Ek plus 1 was being selected by that Kruskal's algorithm, at that time the age E was also available, but the algorithm didn't select that age. And by the construction, the algorithm always selects the minimum weightage, right? So that means that the age Ek plus 1 was selected because of it had smaller weight than E, right? So W Ek plus 1 is smaller than or equal to E WE. Now, but this implies that the weight of T dash is smaller than the weight of T star. How? Because we have actually subtracted a weight which has larger weight and added an weight which is smaller, right? So T dash actually has a smaller weight, or at most the weight of T star. But T star is actually an MST, so its weight cannot be greater than the weight of T dash, right? So the weight of both T dash and T star are equal, and this proves that T dash is an MST. Now, but what is special about T dash? T dash has first k plus 1 edges matching with those of T. So this is actually a contradiction, because we started with the assumption that T star is a minimum spanning tree having the maximum possible number of edges that match with the output T. So in that we assume that there were first k edges which were matching, but in this T dash we have got first k plus 1 edges which match with those of T. So this is a contradiction, and therefore the second possibility that k is less than or equal to n minus 2 is not true, and hence the first possibility there, that means k is equal to n minus 1, that is T has the same weight as T star, and hence T is a minimum spanning tree. So thus far we have proved that Kruskal's algorithm works correctly. Okay, and now we come to another algorithm by Robert C. Prim. So he was also a contemporary of Kruskal. He lived from 1921 to 2021. He only died very recently. He also received his PhD degree from Princeton, in fact in 1949, and Kruskal received PhD degree in 1954. Rob Prim actually served as Director of Mathematics Research at Bell Laboratories, and he was also the Vice President of Research at Sandia Corporations. So the algorithm that Prim published was actually in the year 1957. So this is just 1 year later than the Kruskal's algorithm. So you can see that because of some administrative positions, Robert Prim was actually not able to publish his algorithm, but they might have actually developed the algorithm during the same time. And more interestingly, the Prim's algorithm was actually discovered much earlier than Prim discovered. Actually, it was discovered by a sage mathematician called V. Jarnik in 1930. And it is also said that this algorithm was also discovered by another mathematician called Dijkstra. So there is a lot of controversy around this, and sometimes this algorithm is also known as Prim-Jarnik-Dijkstra algorithm. But we are not going to enter into that domain. Our concern is what this algorithm is and how it works. Okay. So the Prim's algorithm's idea is actually just opposite of Kruskal's algorithm. Kruskal started from just a forest and just build a spanning tree by keep on adding edges of minimum possible weight without creating any cycle. The Prim's idea was just different, just opposite. He started with just a spanning tree having just one single vertex, and he thought that there could be how to grow that spanning tree using, say, only by assuming that there are edges, by just adding those edges from one end point. That means you start with just one spanning tree, one single node tree, and just keep on adding edges that have exactly one endpoint, and there are no other endpoint. So when an edge is added in T, it is just selected, just like in Kruskal's algorithm. The edge must have minimum possible weight, and instead of selecting any edge, we have to select only those edges which are adjacent to the existing tree. Right. So some tree is there at some point, and then we just construct a set that is neighborhood of that tree, and from that neighborhood the vertices are selected one by one. So this is the idea of Prim's algorithm. So why the Prim's algorithm works differently, and why it just actually works correctly, that's a different matter, and can be proved very easily. So first let's look at the formal way of representing this algorithm. The algorithm is given here. So it just takes two sets the set V and the set E. The set V contains just single vertex in the beginning, and the set E is actually an empty set. So E collects the edges of the spanning tree which is being constructed, and the set V is just the set of vertices of the spanning tree. So initially R is just one vertex which could be chosen arbitrarily. There is no restriction how R is chosen. We can start with any vertex. So once that vertex is chosen, we just apply the while loop. This runs as follows. While mod E is less than n minus 1, again here n is just the number of vertices in the graph. So while mod E is less than n minus 1, we just perform the following steps. Now what these steps are: pick an edge UV with exactly one endpoint, and let's say this endpoint be U, which is in V, in such a way that UV has minimum weight. And now once that edge is selected, we add the edge vertex U to V and the edge UV to E. So we have to keep on performing these steps as long as the set E has fewer than n minus 1 edges. So let's repeat this process once again. What this algorithm says: while E has fewer than n minus 1 edges, what we do, pick an edge UV with exactly one endpoint, let's say U, in V, such that UV has minimum weight. And once that edge is picked up, we just select, we just insert U into the set V and the edge UV into the set of edges E. So this way, so when there is just one vertex, so in the second step what happens, all the neighbors of that vertex, say R, all the neighbors are scanned, they are visited. So and the one with the smallest weight is selected, right? So once that edge is selected, that is added to the tree. And in the second step, now there is one edge, right? So in the second step, we just check all the edges that are incident on this edge, right? And just pick the one which has the smallest weight. So this way we get another edge. So that edge is also adjacent to the first one. So we get two edges, two adjacent edges. And third time, we just have to select an edge that is adjacent to any one of the endpoints of the two edges, right? So this way we are actually growing the spanning tree right from the single node. So the one property that is totally different from Kruskal's algorithm is that while Kruskal's algorithm maintains a forest at each step, in Prim's algorithm we are just starting with a spanning tree and just maintain the property that is connectedness. So at every step the subgraph that we are growing is actually connected. And also it is acyclic. Why? Because we are selecting only those edges which have one endpoint in the current subgraph. So at no point there will be a cycle. So we are actually, what we are doing, actually we are just proving the algorithm, because at each step the tree is grown in such a way that the connectedness remains intact. So that at the final step also the output is a connected subgraph, and it is also cyclic. Why? Because at each step we are adding one edge, and in such a way that that edge has exactly one endpoint. So this way this algorithm never creates any cycle. Okay, now it remains to show that this algorithm works correctly. I mean, the output is actually a minimum spanning tree. So we have just shown thus far that the tree is the output is a spanning tree, but its weight is not yet proved to be the smallest. So for this, what you have to do, we can apply the principle of induction. So say at n equals to 1, that in the starting step, the tree contains just one vertex, right? So it is a spanning tree for that subgraph. And then assume that at any subgraph having k vertices, the tree obtained is a minimum spanning tree. So assuming for the kth step, we have to move to the k plus 1th step. And since the tree is at kth step is a minimum spanning tree, and when we move from k to k plus 1th step, we are actually adding one edge, and that edge is having minimum weight. Okay, so we are adding the possible from among all the neighbors of that tree, we are adding the edge having the minimum possible weight. So this way, the tree that is obtained at the k plus 1th step also has minimum possible weight. First thing. Second, the weight also, the tree that is obtained is actually minimum spanning tree, because it is not, there is no cycle in it, right? So we have just actually proved that the Prim's algorithm works correctly. And now let's look at an example. So look at this graph. It has 8 vertices, and the graph is weighted and connected. So we start with, say, vertex V1. So initially there is only just one vertex in V, and there is no edge. So we select the minimum possible weight, and that is the edge V1, V7. So we select this edge. Fine. Now, since there are two edges, there are 4 edges adjacent to this, and these edges are V1, V2, V7, V2, V7, V3, and V7, V6. The 4 edges V1, V2, V7, V2, V7, V3, and V7, V6. So among the 4 edges, we have to select the one which has the smallest weight. So this one has the smallest weight, V7, V3. So we pick this one. Okay. And then now the tree has 2 edges, right? So there are many edges that we have to consider, and these edges are, say, V1, V2, and V7, V2, V3, V2, V3, V5, V3, V4, V3, V6, and V7, V6. So we have to consider all these edges, and among all these edges, the one having the minimum weight is, there are actually 2 such edges, that is the edge V1, V2, and the edge V3, V6. So we can select any one of them in this case. So let's select V1, V2. Now we cannot select the edge V2, V3 because its both ends are there. Both ends are in the tree. Likewise, we cannot select V2, V7 because its both endpoints are in V. So we are now left with the edges V7, V6, V3, V6, V3, V5, V3, V4, right? So only these 4 edges are left, and among these 4 edges, the one with the smallest weight is V3, V6, right? So we just select this one. Okay. Now we are now you can see that the edge V7, V6 cannot also be selected because its both endpoints are already there. So now now there are the possible edges which could be added are V6, V4, V3, V4, and V3, V5. These 3 edges are there. So among these three ages, the one having the smallest weight is V6, V4, right? So we select this one. Fine. And now the age V3, V4 cannot be selected because both of its endpoints are already there. So now we can, there are three ages among from which we can select. This is V3, V5, V4, V5 and V4, V8. And among these ages, the smallest one is V4, V5. So we select this one. And then we cannot select the age V3, V5 because its both endpoints are already there. And now we are left with two ages, V5, V8 and V4, V8. So among them, the one with the smallest weight is this V5, V8. So we select this one. So this is the output of the Prim's algorithm. The tree that we have got is having the ages V1, V2, V1, V7, V7, V3, V3, V6, V6, V4 and V4, V5 and finally V5, V8. So you could see how the construction differs drastically from the Kruskal's algorithm. If you had applied Kruskal's algorithm on the same graph, say you would select the first age to be say V1, V7 and then second you could select also either for V3, V7 or you could select V5, V4, right? Because these three, in any case, the first three ages selected by Kruskal's algorithm would be V1, V7, V3, V7 and V4, V5 because these are the ages having the smallest weight. But it is not the case with Prim's algorithm. Prim's algorithm is just grows in such a way that the connectedness property remains unaffected. So this is the major difference between Prim's algorithm and Kruskal's algorithm. Apart from now, if you just talk about the complexity of these algorithms, then simply suppose you wish to implement Prim's algorithm. So how would you implement it? Because say the ages are unordered, say some they are given in some array, and we have to there are two ways. Either we can just sort them, which is just the simplest way. So we can just sort them using some sorting technique, and then we can pick one by one the ages. So the outer loop of that, the while loop that Prim's algorithm has, just runs at most n minus 1 times, and sorting of those ages requires in worst case 1 square time. So the time complexity of the algorithm becomes O n cube. But I mean, this is the worst case time complexity and of Prim's algorithm as well as of Kruskal's algorithm. But there are efficient implementations which you can achieve by using efficient data structures, and some data structures that are used actually for implementing these algorithms are disjoint set data structures, which we shall not discuss here. So one can apply these algorithms. These algorithms have very wide applications. The minimum spanning tree problem actually arises naturally in real world situations where a graph is given and one has to construct just a route from one vertex to all the remaining vertices, and that route is constructed in such a way that one has to travel a minimum now in terms of say the age weights. So for that kind of problems, minimum spanning tree algorithms are quite useful. So now we just come to the end of this session. Let's briefly review what we have discussed here. we started with the problem of what is a minimum spanning tree, and we described what is minimum spanning tree problem, and we looked at how this problem could be solved, what are the conditions under which this problem has a unique solution. So we looked at theoretical considerations, and then we discussed two fundamental algorithms for finding minimum spanning trees in weighted graphs, and given by mathematicians Kruskal and Prim. So these algorithms, we also discussed about the correctness of these algorithms. We proved why these algorithms work correctly, which is very essential for any algorithm, in fact, because if you do not know whether the algorithm works correctly or not, there is no point in applying that algorithm. So one has to just take care of, be cautious about the correctness of algorithm. We discussed that, and we described these algorithms in detail using examples, and we looked at how these algorithms could be implemented using some data structures. So that is what we discussed in this session. There are many other questions which one could ask, like what are the conditions under which when the weights are there are many variations of this problem. So for instance, instead of finding minimum spanning tree, one could also ask how to find a maximum spanning tree in a weighted graph. So such problem might arise from instead of finding the minimum weight, the problem could be one wants to maximize the weight in the graph, and one might say one could maximize the profit in traveling from one point to all the other points. So in such this is actually the duality problem. So while maximizing the weights, one has to only just modify the algorithm slightly. So instead of now selecting the minimum possible weight, one can just start with selecting the maximum possible weight and keep on selecting edges as long as they do not create cycle. So that kind of possibility is there. One can just look at the variation from minimum spanning tree to maximum spanning tree. In fact, there are many other variations of spanning trees, like one can find minimum diameter spanning trees. So that is a different thing. Here one has to focus on the total the diameter of the maximum distance between any two vertices of a spanning tree. Again, that distance could be measured by the weights on the edges. So that is all for this session. We end this session here. Thank you.